Hello, everyone. I think we're going to get started. This is Lisa Andrews with AWS Truepower. I'd like to thank you for joining us and welcome you to today's webinar to learn more about the operational analysis of wind and solar projects and how uncertainty is reduced on energy estimates with operational data. So just to let you know, this is the second webinar in a series of 3 that AWS Truepower has been doing on wind and solar project finance and the technical aspects of project evaluation. The first one was an overview of the technical due diligence process, and if you didn't catch that, it is available on our website. And the third webinar, which is coming up on December 6th, in that we'll be discussing the portfolio effect for renewable energy projects, and that is basically how uncertainty is reduced when multiple wind or solar, or wind and solar projects are combined and assessed as a portfolio. So if you're interested in that one, you can go to our website and follow the registration link to that one as well. So presenting today will be Brian Kramack. He's a senior project manager, and Josh Kunkel. He's a business development manager for our investor services group. And just to help you understand our approach to this topic today, we've prepared the webinar content really to address the most common questions that we get asked about operational analysis in the hopes that it will also answer your questions that you may also have on the topic. So we're going to start probably with Josh helping to summarize the reasons why customers are currently coming to us to do operational assessments. And then Brian is going to focus on answering the remaining questions that are listed on this slide. But before we do that, I just wanted to note a couple of things. This webinar is presented in listen-only mode. We do plan to answer questions at the end of the webinar, so please enter any questions you have into the box on the GoToWebinar interface during the presentation. We'll do our best to answer them given the time allowed at the end. We're also recording today's webinar, and we will make that recording and a copy of the presentation slides available, so we will email you when those become available. Okay, so with that, I'm going to hand it over to Josh to get started.
Great. Thanks, Lisa. Yeah, we certainly have seen a growing trend in the industry where plants are conducting operational energy assessments, especially as more and more plants are coming online, being bought and sold and so on. So we feel like this is a rather timely topic. We're going to go ahead and try and give a full spectrum of information here, starting with some high-level whys and hows, and then digging in to provide some technical detail on the specifics of our process. First, we want to give a brief overview of AWS Truepower and who we are. AWS Truepower was founded in 1983, giving us nearly 30 years of experience in the rather young industry of renewable energy. We offer a broad range of services that support the full life cycle of both wind and solar projects. And to date, we've provided services on over 60,000 megawatts of renewable energy in projects spanning 80 different countries. We have about 100 employees here at AWS Truepower, with close to 80 of them meteorologists or engineers. We're headquartered in Albany, New York. We have offices in Barcelona and Bangalore, India. So with that, let's dive in. As I mentioned earlier, we've seen a strong trend in the recent months and years for owners of operational plants to reassess the energy potential of their wind and solar assets. The real advantage in doing this is the ability to create a more accurate picture of what the plant will produce based on actual operational data, whereas the pre-construction energy numbers relied solely on models. This is an important distinction. The energy number calculated before the plant was built, while we fully expect it to be accurate, may need to be updated based on how the plant is actually performing. There are obvious benefits of closing this gap between the energy number predicted by the pre-construction forecasts and the actual energy numbers once operational. Whether the plant is underperforming or overperforming, correcting the financial models with a more accurate picture of revenue production is always prudent. However, even if the plant is performing as predicted, there are still benefits in having an operational assessment performed. Because the new energy number will be based on actual data, the uncertainty around the energy production moving forward will be reduced, in some cases as much as half. So this is another point to drive home. There are 2 real advantages to having an operational assessment done. One, you'll have an updated, more accurate P50, which is your best case energy number, and used to calculate the net present value of the plant. Secondly, you'll be able to decrease your uncertainty around your P50, meaning that you will end up with a tighter uncertainty distribution, higher P90 and P99 values. This P99 value is oftentimes used to determine the plant's debt capacity. This is one of the strong drivers we're seeing in the market right now. As more plants become operational, many start approaching the 5 or 10-year mark, many are looking to refinance. In some cases, the equity stakeholders of these plants have reached the end of the tax credits, or perhaps the owner simply would like to refinance under more favorable terms. In any case, they really need to look to increase the P99 and P90 values. Another driver we are seeing is very strong activity in the mergers and acquisitions market, where owners are packaging up wind and solar farms with more accurate energy estimates and selling them as a portfolio with an overall lower uncertainty. There are a few interesting market trends that are leading to strong M&A activity and market consolidation. The most prominent factor is the pending expiration of the PTC at the end of this year. Now with the election over, hopefully the coming weeks will lend more insight into the status of the wind tax credits, but the uncertainty looming over the wind industry has led to reduced pipelines in 2013. On the other hand, market uncertainty aside, the wind market is actually becoming more attractive to larger, risk-averse companies and more traditional investment methods. The market is becoming more mature and has a track record now that allows insight into performance and potential risks. The cost efficiency of the technology is improving, while the demand for many companies to include renewable energy as part of their portfolio remains strong. This is leading to large, established companies increasing their share of the market, or in some cases entering the market, through acquisition of wind assets or companies with wind assets. While the solar market is not experiencing the same level of uncertainty regarding government policy or the same level of M&A activity, many of the solar assets are packaged together with wind assets in portfolio acquisitions. In fact, adding solar assets to wind portfolios can further decrease the uncertainty of the entire portfolio as part of the portfolio effect. As Lisa mentioned, this will be a topic we'll cover in depth in our next webinar. So, whether it's a plant refinancing or a straight acquisition, a new operational energy assessment should be conducted in order to provide a more accurate picture of the energy production and reduce overall uncertainty. So let's look a bit here at some of the differences in how pre-construction estimates and operational estimates are conducted. In a pre-construction estimate, monitoring systems are put up to measure wind speed or solar radiation, along with other valuable meteorological data. And this data is used to predict future energy production at the site. A simple site with flat terrain and a small number of wind turbines can often go to financing with a single year of high-quality measured data. The site is more complex, whether it's more complex terrain or simply a larger site, the number of monitoring systems and the length of the measurement period should increase in order to reduce uncertainty. In an operational assessment, each one of the turbines or solar modules acts as an individual monitoring system for that location. So, for example, let's say a 50-turbine planned wind project has one Met tower monitoring for 3 years before construction. That gives 3 years of total data that will be used to assess the resource before it's built and to obtain financing. Now, once operational, each turbine acts as a monitoring system. After operating for 1 year, the site now has 50 years of wind speed data, 1 year of revenue meter data for each turbine that can be used to assess the energy potential moving forward. Since we already know the energy generated, it eliminates a significant number of assumptions and their associated uncertainties. In a pre-construction estimate for a wind project, you normally measure wind speed at some low elevation and have to extrapolate to the wind speed to the hub height that drives the wind turbine. Also, because you will only have a few Met monitoring stations, you'll then need to extrapolate the wind speed from each Met mast to each turbine location. You then need to calculate the effect of the varying terrain on the extrapolated wind speed, the amount of energy each turbine will extract, and how this affects each turbine's ability to produce energy. In addition, availability of the turbines, electrical losses, and a variety of other factors must be accounted for to arrive at an energy number. However, with operational data, all of these extrapolations, assumptions, and associated calculations are already accounted for. The revenue meter data at each turbine provides insight into all of these factors, and therefore, the uncertainty moving forward is greatly reduced. So, Brian, can you take us deeper into the analysis? When in the project life can we do an operational assessment?
Well, Josh, some types of operational assessments, such as performance testing, they can begin as soon as the plant's operational. The type of assessment we're going to discuss today, that requires that the plant be operating in a stable manner. Just like resource assessments that are conducted before the wind or solar project is built, operational assessments generally require 12 months of data. However, if you consider the initial plant downtime and startup issues, commissioning issues and such, it might take up to 18 months of operation to get a year's worth of usable data. The same is true for solar projects. It might take more than 12 months of data collection to generate a complete one-year data set. For example, a larger project might be commissioned in several phases, or regions with snowfall may lead to gaps in the data records. Let's look at the information that's required to do an operational assessment. As we mentioned a few slides back, revenue meter data is one of the primary building blocks that we use in our operational assessment. In addition to the revenue meter data, we need availability data, not just the turbine availability, but the measurements from the SCADA system used to calculate the turbine availability. The turbine warranty agreement makes distinctions for categories of time or energy that do and do not count in the contractual availability definition. We use this turbine availability data to calculate a plant level availability that takes into account the lost time or energy that might not necessarily count against the turbine manufacturer, but it is needed to determine the time or energy actually lost during operation. What we really need to know is how much energy could have been made, as if the project were fully operational. In order to determine this, we need to account for all the time or energy lost, not just contractually allowed time or energy. Now, we've mentioned both time and energy types of availability accounting. Many turbine manufacturers are now accounting for energy lost, not just time lost. Energy-based parameters yield a more accurate regression for this type of analysis than the older time-based parameters. Why is energy more accurate? It's because time does not equal energy. The energy lost during an hour when the turbine is down for maintenance, when the wind is only blowing at 2 meters per second, is probably 0 megawatt hours. But the energy lost when the wind is 15 meters per second will be much higher, probably the full rated capacity for all the turbines that happen to be offline. But one of the things to take into consideration is that these energy-based parameters can be biased if they're using the advertised power curve. Energy loss calculations will be much more realistic if they're based on the average of the power curves from turbines tested at that particular site. We've listed nacelle wind speed here as well, but we have done the analysis without it. We like to include it in the analysis as it allows for the best calculation for the windiness on the site. The on-site met mass could be our best reference station, but we can only use this data under controlled conditions. We'll get into the specifics for that in just a few minutes. Finally, we have turbine generation information. This is optional, but if it's provided, it'll be used to calculate the average electrical loss between the turbines and the revenue meter. For solar plants, in addition to the SCADA data for the actual generation, meteorological data is collected from pyronometers distributed across the site. We also look for temperature and wind speed measurements, as they are key elements in the analysis. The maintenance practices on the instrumentation itself are also evaluated to ensure good data quality. The operational reports are the most important input, operational reports are also another important input, other than the actual operating data. Good operating reports summarize project activities. They provide information on what actually happened at the site during a given period. Reports on a monthly basis are the most common. Turbine and module as-built coordinates are required, so we can include in our report. The coordinates do not necessarily play into any of the calculations. We simply use them to show the farm layout in relation to the local topography, and also to show the relationship for the equipment to the on-site meteorological instrumentation. Finally, we need our reference station data. The client is only involved with this aspect if we're using his on-site data. Otherwise, we evaluate different sources of public and private ground-based or model data for use for our reference stations. If we're using on-site meteorological data, we also need the commissioning forms for the equipment that were used to collect the data. It helps us understand what equipment was used and allows us to verify that the equipment was properly set up. For solar project, pretty much the same requirements apply. We like to see the operational reports and the commissioning documents for the plant equipment as well as the meteorological equipment. As far as solar reference data goes, we're looking at the same parameters. Ideally, we look for reference stations with good quality solar radiation, temperature, and wind speed measurements. Let's talk a bit about the different types of reference station data and where you can find it. There's several sources of reference station data. If you have an operational farm, consider purchasing one of our virtual met masts. We call them VMMs for short. These VMMs are interpolated to the location of interest somewhere on your farm, and are based on the same data used to make our maps, also available on our website. Depending on your location, you might also be able to use data from airports, and that's the ASOS data that we've referred to here, or also data that's been modeled by NASA. It's referred to as the MIRA data. As we mentioned before, you can also use your on-site wind speed data, but problems can arise from prediction using the on-site Met towers if those Met towers are waked by turbines, and we'll cover that in a second. On the solar side, high-quality reference data near the project site is often more difficult to come by, and the data isn't of consistent quality. We have to be very careful in selecting reference data compared to site-specific solar radiation measurements. There are various satellite-based models available that we can use. While the accuracy of these models is lower than the surface measurements, they usually have a longer period of record and are generally available for locations that might not have actual surface measured data. Let's go take a look at what makes a good reference station. The most significant check that we do is for the lack of trending on an annual basis. In the example on the left, 3 of the 4 potential reference stations had significant trends that made them unusable. The example on the right shows 3 reference stations that we would have considered usable for this type of an analysis. If considering on-site Met data, this becomes one of the most important checks. You need to confirm that the wind speeds before and after the installation of the wind turbines are not significantly impacted by the turbines, from the wake of the turbines. And that's done by looking for proper tracking and correlation with some off-site regional reference. We've talked about all the data inputs. Now let's discuss how they're used to generate an energy estimate for the site. Here's the 50,000-foot view. We make corrections to both energy and wind speed to make them representative of their full potential, normalizing to allow the best use of our linear regression. For energy, this means we're correcting for availability and curtailment, and that's to arrive at an idealized energy as if the farm were operating at 100%. For wind speed, we make an adjustment to account for seasonality, the differences in temperature and pressure as compared to other times of the year. Now, this regression could be done on any of several different timescales, depending on what data is available. So let's look at the different analysis periods we could use. For us, we found that the use of monthly data is the best, and it's primarily for 2 reasons. First, it's most often the data that's available. A lot of times we're in a data room. There's summaries available in monthly reports, especially for finance jobs, and it's the information we're most likely to come by. Second, because the analysis can be done with a simple linear model. This is easier to look at. This is easier to understand if you're actually looking at some graphs. So let's look at some examples. Here's just 6 months worth of wind speed and energy data from an example wind farm summarized in 10-minute, daily, weekly, and monthly intervals. It is clear to see that the monthly and weekly data are linear. That's the 2 on the bottom. And that the daily and 10-minute data follow the Para curve, and that's more represented by the S-shaped curve that you would see for a turbine. As Josh explained in the beginning, our reports are often used for refinancing or to establish equity value as part of an acquisition or merger. It is important that the method used be understandable and comparable to industry norms. Our operational assessment is designed with these key factors taken into consideration. Let's take a quick look at the weekly time period, as it also demonstrates a linear tendency. This comparison is a summary of several different reference stations. They're from different locations, and they're from different types. Some of them are ground stations, some of them are actually hub height modeled data sets. And what they show is that the monthly period of record data is more likely to be representative of historic data than weekly period of record data. There is more variation in the weekly time series data than there is for monthly data, and that's just because it's averaged over a longer period of time. For this analysis, we're basing future estimates on the fact that the period used is representative of similar periods of historical data. The monthly data best supports this assumption. Now, we've discussed the data that's used. Let's dig a little bit deeper and talk about the mechanics of the analysis, how the process works, and how we're actually going to do the adjustments and calculations. So how does the process work? The process can be generally described, and we actually describe it the same way for our pre-construction estimates, as measure, correlate, predict. And here's some of the major steps for each one of those is outlined next to each one of the topics. Both wind speed and energy data in the raw form are useful. As we discussed, adjustments need to be made to remove the influences that are known to cause the regression model to be weaker and less accurate. We're going to be covering those in the next few slides. Let's start off with availability. Adjustments, they're just made through a series of simple calculations. To adjust for availability, simply divide the actual energy produced by the planned availability. Note that it might take some work to get good planned availability data. That's different than turbine availability, and we've already touched on this. To adjust for curtailment, if there is any, add it back to the monthly value, which we've already have after we've corrected for availability. Finally, to adjust the energy for the number of days in the month, multiply by a standard month length. We've used 30, as you can see here in this formula here, and divide by the actual number of days in the month. This removes the length of the month as a source of variability in the regression. These are the only major adjustments that are made to the energy data used in the regression. There are special cases where energy loss for other reasons is tracked separately, but they're outside this more basic discussion. Now that we've made the adjustments to the energy, let's look at how seasonality can be addressed by making adjustments to wind speed. Now, in this calculation, V is for the wind speed or velocity, and rho is the density. If the density for a 10-minute record is higher than the density for the long-term average, the effect is an increase in the wind speed under the IEC calculation used in turbine performance testing. What we've done is taken the exact same formula, and instead of 10-minute records, we've applied it to our monthly data. Simply put, denser air means that there's more energy when compared to less dense air. To normalize for density, when the only parameter is wind speed, you have to take wind speed and raise it slightly for the measurements taken with the denser air. And this equates to more energy when compared to the turbine response. It's a minor adjustment, but this has been shown to reduce the influence of temperature and seasonality on data used in the regression. And it usually results in both a lower error and higher correlation and coefficient of determination. Let's actually look at a couple examples here. Here's some examples of the wind speed and energy data in a scatter plot with wind speed on the x-axis and energy on the y-axis. All the adjustments we've been discussing have been made already. The regression slope and offset are given if you add a linear trend line to the scatter plot. In Excel, the regression tool for the data from the data analysis toolpath can also be used, and it results in a more complete statistical analysis. The same regression tool can be used to do a multiple regression using two different reference stations. If a single reference station isn't achieving the desired results, the tool provides both the slopes for both of the wind speeds as well as the combined offset or intercepts. Now, Excel can't handle multiple regression plots, but you can use a statistical open source package called R if you need a visual depiction. R has a couple called R Commander, and if you use these two packages, you can get they can be used as a method to generate the plots associated with the multiple regressions. In this case, the left-hand view is similar to what you would see in a single regression, and it's clear from the data is tightly grouped vertically, showing that it's associated tightly with both wind speeds together. Now, if we take that and we spin it so that that allows us to look at how the wind speeds on the two axes, one to the right and one to the left. The one to the right is actually a ground-based station, and the one to the left is a modeled set of data. That's actually our wind trends data. It'll let you see that the lowest wind speeds in this case happen to be better correlated with a ground-based station and the higher wind speeds were better represented by the modeled site data from our wind trends model. I think this is a good point for Josh to summarize some of the key trends that we see when we're doing this kind of analysis.
Sure. I think it's helpful to understand some of the basic features of this type of analysis. Many of the observations seem intuitive, especially when considering the interplay of different sources of information. The fact that the corrected data has a stronger correlation than uncorrected data is intuitive, especially now that we have an understanding of why the correction was made. If you are doing this type of analysis with your own data, you should see similar results. If you don't, go back and check your adjustments. Make sure that the potential reference stations are properly aligned with the energy data. It's also usually the case, the closer you are to the actual wind energy interface, the stronger the regression. Using turbine energy should result in a stronger regression than revenue meter energy, which makes sense because the variations in electrical losses are excluded. Another point, the wind speed aggregates from the nacelle anemometer will most likely result in the strongest regression with energy, but since there is no historical data, they can't be used for energy projections. But the nacelle anemometer wind speeds should correlate nicely with the reference station selected, as should the energy data. Of course, there are exceptions, but they are rare and often explainable once you dig into the data. So, Brian, how exactly is the regression used to predict energy?
Well, for that, you got to remember back to your algebra days, and we're going to go to the good old formula y equals mx plus b, where m is the slope and b is the intercept. The regression model that we've used has given us these same terms. We simply input the average long-term monthly wind speeds from our reference station, adjusted for long-term average density for that period. In the beginning, we discussed normalizing to 30-day periods. Now we need to undo this adjustment and scale the months to their appropriate lengths. Once this is done, we can sum the monthly gross energies. The end result, when we sum these monthly gross energies, is an annual gross energy that has taken seasonality into consideration, but we still haven't addressed availability or curtailment yet. The gross energy multiplied by the curtailment, multiplied by the expected future plant availability, and then adjusted for curtailment, will bring us to the net annual energy that is comparable to that calculated using pre-construction methods. So far, we focused primarily on wind project operational assessment. So we're going to take a minute and have a look and talk about the similarities and differences with solar projects. Solar plants experience two types of degradation: an initial power output stabilization period during the first few hundred hours of operation, and then separately, a degradation of performance over the project life. Initial stabilization is usually included in the module nameplate power rating, but this loss is not included in this analysis. We actually want to skip it because the loss is already accounted for in the actual operating characteristics of those modules. The long-term degradation rates are applied in a similar annual fashion as pre-construction estimates. Planned outages and weather events may also impact the consistency of the data. Snowfall during winter months can cause data to be artificially skewed if, for example, a pyranometer would have been kept clear, but the modules had been covered. These outlier data points would bias the long-term projection and therefore need to be removed. Calculating daily performance ratios can help flag these data points for further analysis and to allow them to be removed from the monthly analysis. Once long-term energy production is estimated, losses due to availability and snowfall still have to be addressed. Depending on the site conditions, location, and the availability of operational data, either daily or monthly regressions can be used to represent the site. Like the regression analysis explained earlier for wind projects, different timescales can be used for solar projects. As a comparison, monthly regression could be used for an Arizona project with mostly sunny days, while daily regressions might be more preferred for a project in northern climates such as Ontario. It's important to identify the most reliable reference data source in order to perform the climate adjustment. That's the seasonality, that's year to year. This reference data can be ground-based measurements or modeled from satellite data, depending on which most accurately represents the long-term climatology, which needs to have a period of record, typically longer than what the on-site data will provide. Finally, we estimate energy for a typical meteorological year without including that loss factor for degradation. We compute an estimated interannual variability in plant output and monthly production to performance ratios. In order to compute the final annual energy for the typical 25 evaluation period, we apply the estimated performance degradation to the sum of those monthly values. Let's go back now and have a look at some additional considerations for wind operational assessments by looking at windiness. Josh?
Sure. So a single year of operational data tells us a lot about the project's future prospects, but interpreting the data must be done carefully. One of the biggest areas of misunderstanding is in estimating the relative windiness for the period of operation as compared to the long-term windiness for that location. It is possible that during the year of operation that actual wind speeds are higher than normal, leading to higher than normal production. If the effects of windiness are not understood, the increase in wind speed above average wind speed can mask poor operational performance, effectively hiding an underperforming asset. Likewise, the same is true for lower than average wind speed years. The wind speeds may be significantly lower than normal, but the plant could actually be operating quite well. It's important to take a good look at the reference station's historical trends in order to provide an indication of the relative windiness. So let's look at a few observations here. As we've discussed, wind or solar projects are initially developed and financed with modeled energy data. The methodologies used to predict future energy are constantly being refined and updated to reflect current learnings and market conditions. It's no secret that wind farms have traditionally underperformed as compared to their pre-construction estimates. Many of you are aware of our recent extensive R&D efforts to close this gap, and we are continually checking our methodology as more and more operational data is available. These adjustments and the adjustments of other consultants in the industry have generally been downward. That is to say, a projection done now for a farm originally assessed a year ago could be 2 to 4% lower in energy if assessed today. This is seen in the results of our operational assessments. It's not uncommon for us to project energy 2 to 4% lower than a pre-construction estimate prepared, say, 1 to 2 years ago. Now, while the P50 long-term annual energy estimate might be slightly lower than the value reported in the pre-construction estimate, the use of actual revenue meter and plant operational data removes several points of uncertainty, resulting in a significantly lower long-term uncertainty as compared to the pre-construction estimate. The net effect of a more accurate P50, in addition to a lower uncertainty, is generally seen as a higher P90 and P99, all other issues remaining constant. A plant that is performing poorly can't hide behind these common observations. So, Brian, can you discuss the recent advancements in our operational assessments?
Sure. And this is one of the last points we're going to touch on before we sum up and start taking questions. But as far as new methods go, one of the things that we've been looking at is, can we actually use less than 12 months of data? As we said earlier, we need about a year's worth of data to make this operational assessment method work. We also discussed that it can take up to 6 months of wind farm operation to reach, or take 6 months for the wind farm to actually reach mature, stable operation. Well, this means that 18 calendar months could have gone by before there's enough data accumulated to perform an operational assessment, and that's under our current methods. This means that the decision to refinance or to take an equity stake would still need to be based on pre-construction methods for a farm, even if it had 16 to 18 months of data. We're refining our methods, and this is the refinement, and we've been working on ways to allow fewer months of data to be used to deal with this issue. Here's an example of a reference station, wind speeds for a farm that's a candidate for evaluation with less than 12 months of data. Now, as you can see, the wind speed concurrent with the period of operation generally follow the long-term historical averages. And we also have months where we have higher and lower than average high and low monthly speeds. In addition to having a well-represented band, higher than the highest high, lower than lowest low, it's also true that the remaining months fall in the middle. The wind speeds all trend towards the average wind speed for that site. There's no more outliers that we have to account for. We also have to look at seasonal patterns to make sure that they're all represented in the data we use in the analysis. With 12 months, this wasn't an issue. We had the whole year, and we would say that that year would be representative of other years, all things considered. But once we start talking about using less than 12 months, we have to be very careful about temperatures and pressures and the fact that we have seasonality properly accounted for. Another challenge we have to deal with is the smaller data set. It's whether or not the results are going to be statistically significant. If this analysis were done with only 8 months of data, as an example, it's possible to see an R-squared of 0.62 just from random chance. All of the issues mentioned here would have to be addressed in order for this method to work on a specific project. So, wrapping things up, we've talked about operational assessment method, how it compares to pre-construction. We've looked at uncertainty, and we need to understand that this is really about the big picture. There are times when it's very important to study the leaves on the trees, but sometimes you have to look at this forest for itself. Monthly analysis is focused on the bigger picture of average production over a longer period of time. It is akin to seeing the forest, not the trees, for both wind and solar projects. We'll now take a few minutes and see what kind of questions we have, see what questions have come in during the presentation. Lisa?
Thanks, Brian, and thanks, Josh. That was great. All right, just give me a second here to look at some of these questions. Okay, here's one for you, Brian, I think. It says, if you're using operational data, why is there any uncertainty at all?
Yeah, that's a good question. Well, you got to think about it from this perspective, and you're really dealing with two different things. You're dealing with average plant operation, average predictions, and that's what we're going to talk about. That's when we talk about the P50 value. And it's true that if you were to operate the plant for 20 years, well, you could just take the average production, and that would be your estimate of the long-term average. The same is true for 10 years. And there's many cases where if you're looking for some sites with low interannual variability in the wind speeds, it could be that just 5 years would be indicative of the actual average operation for that plant. Now, that's the average. That's not the uncertainty that this one question is asking about. The uncertainty has to take into consideration the things that are changing and the things you can't account for. Even when you've taken a lot of data, like 10 years, you can't say that has accounted for some of the future variability in the wind speeds. And you can't say that it's accounted for the changes in availability of the turbines themselves. These are the different things that still factor in, and you just can't get rid of them. They're always going to be there. Actually, that brings up a good point, and we didn't touch on. One of our assumptions for availability is that once we've determined what the average availability is going to be, we assume that you're going to operate that plant as if you're always going to maintain that availability. So over time, that would mean that we're expecting you've adjusted your budgets and that you're spending the money on O&M to allow for the opportunity for you to maintain that plant level availability. If you haven't accounted for that in your financial models, if you haven't accounted for that in your in your actual O&M budgets, and you're going to let the O&M budget tail off, then we're going to have to make some other kind of an assumption for availability, and that's just going to increase the uncertainty. It's another one of the terms that would increase uncertainty. I don't know if I rambled on a bit there, but hopefully that answers the question. You got another one?
Yes, we have more. Okay, Josh, for you, I think there are many references to P99 and P90. Can you explain what they are and how they are related to this presentation?
Sure. Yeah, we really didn't define p-values as they're called, and I believe we touched on it in our last presentation, and we'll go through it a little bit more in our future one. But essentially, the p-values are your probability of exceedance. So if you have say a P50 energy number, that is saying that there's a 50% chance that that wind plant or solar plant will exceed that value. As you start adding uncertainty, the p-values will shift from P50 to P75 to P90 or P99. If you look at the other end of the spectrum, your P99 says that there's a 99% chance that that plant will exceed that energy number. So it's a way to account for uncertainty. P50 is generally going to be your best case, highest energy number.
Okay, thank you, Josh. Another question, you mentioned that you do use 10-minute data for some types of assessments. When do you use 10-minute data?
Okay, I'll take that one. And actually, there's a couple other questions I see on the list that are kind of related about dailies and weeklies. I'll try to wrap this up all into the same question. Let's see. From a 10-minute aspect, one of the things that we developed a while back, I think it was 2 years ago, we developed an engine called SHARP, and that's our System Health Analysis and Reporting Program. And we actually use that, and we use the 10-minute data, but we normally do it like that last pretty tree slide thing. We use it to look at the leaves and not the trees. If we've got a question on a specific issue, we might use SHARP and the 10-minute data to drill down and really figure out what's going on with some particular performance aspect. The big one that's come up twice in the last year is curtailments. In one case, we had a farm owner that wanted to know what his curtailments actually were to see what they figured in. And then in the other case, we had an ISO, one of the independent system operators. Well, their PPA, their power purchase agreement, required that they actually pay for curtailments of certain types. So they curtailed this one specific farm, and then the farm put in and said, here's our energy that you curtailed us by. Well, we can use our SHARP engine to analyze their SCADA data to see if that estimate's reasonable. So that's an example of how and when we would use different periods.
Thanks, Brian. We have time for a couple more. Another question. I didn't understand the comment on windiness a couple of slides back. Can you go back and talk about it again?
Yeah, I'll take that one. Can you back the presentation up a couple slides? Yep, that's the one. Okay, so with this slide for the windiness, what we were trying to draw the comparison between is the farm operator or that's looking at his own data. He actually has 2 years of data, and he's looking at his 2 years of data, and he says, you know what, my operation's been really good. Things are operating swell, and we think you should look at our actual because it's so much better than our pre-construction estimate. And the fact is that if you had a period of extreme winds, and it is possible to have winds above average for 1 and 2 years at a time, if you find yourself in that position, it's better to have the operational assessment done, especially if you're looking at investing in a facility where all of a sudden their energy number is higher than their pre-construction estimate by a significant amount. Because that operational assessment will go in, it'll account for the windiness, it'll establish a baseline, and it'll let you know on a level playing field how that farm's been performing. In this case, you can see on that, in the left-hand graph on the right-hand side, that right-hand column, you can see that for this one example, availability might have been a little bit low, and actual performance, once accounting for wind, would have been lower than what the pre-construction estimate was. Now, the same can be true of low wind. You don't want to penalize a wind farm just because it's been a couple low wind years, and the only way you can actually do that is to go check and see what the wind speeds actually were. So I think that answers the question. I see another one here about 5 years of data being enough. I assume that that's about on-site wind speeds or on-site solar data. Yeah, generally 5 years would be enough. It really depends. We compare it to the regression, or we compare it to the other reference stations. As long as the trends are there, there's no negative trends, and they're trending the same over the entire 5 years. 5 years for on-site data might be enough. There was another one about forcing the linear regression through 0, 0. No, we don't force the regression through 0. We actually account for them. Remember, we're not dealing with exact calculations of energy. We're dealing with the reference station as a forecasting device. Energy is not calculated from the reference station. The reference station is just, we're determining its capacity to forecast what's on to be related to the wind forecast. Go a little bit farther up. I think that's it. Yeah, there's a lot of these other ones are a little bit, a lot of these other questions are more detailed. So if it's okay, I think we should wrap those up. And Lisa, I think you were going to cover how we're going to handle our final questions.
Thanks, Josh and Brian again. But we do have some more questions, but some of them are a little more complicated. And I think what we've done before and what we'll do with this one is we'll put that list of questions together with some written answers, just so they're clear for everybody, and we'll circulate them all to the entire list of registrants. So in closing, I'd just like to thank you all for joining us. We really appreciate it. And we hope you'll join us for December's webinar on portfolio analysis. So that concludes the webinar. Have a great day, everybody. Thank you.